Well, thanks very much. I am very sorry I couldn't join you in person today. My name is Emre Kujaman. I am a senior principal researcher at Microsoft Research. I'm very happy to be able to talk to you today about the work we've been doing on an open source suite of causal AI tools and libraries. Um, During this talk, I'm going to try and cover 3 points. One is the importance of causality for decision-making applications. Second is I'll review, of course, our tools and what we're doing to try to make it easier to apply causal inference to decision-making applications. And finally, I'll briefly touch on a number of common usage scenarios that we're seeing out there, both from our first party experience as well as from what we're seeing people use this for in the broader community. So let me start by reviewing a little bit about what a causal question is, what some of the causal tasks that we see are. And really, a causal question or causal task, it's an analysis task that is focused on a cause and effect relationship, usually where we want to analyze or make some change in the world, and we need to know what the effect of that change is going to be. For example, we have customers who are asking about the impact of their actions and trying to understand how they can optimize their business. We have partners in agriculture and retail and across industries, really, asking about key decisions related to fundamental business processes related to climate change. And in health, questions arise about how we can more rapidly advance our knowledge of the basic science, public policy, and clinical decision making. These are just a sample of the broad variety of causal questions we are seeing our customers and partners asking. Um, and while while today's methods have begun to have a real impact in the world, it's also true that causal AI as a technology is still early in its development. And we know that this research area is going to require many more advances and iterative practical deployments to reach its full impact. And so we believe that fundamental research is accelerated when it's motivated and informed by considerations of use. And so to enable and accelerate this kind of use-inspired basic research and causality, we want to create mechanisms that help us enable and ease the practical usage of state-of-the-art technology and also collect the learnings from that, the challenges to inform the directions of basic research. And that's really the motivation for our work in this open source library. It's both to enable the practitioners as well as to learn to inform where we need to be applying our research skills. So I just want to say why are these types of why do we need something special? Why do we need something called causal AI or causal effect inference? Why can't we just use regular correlational machine learning methods? And the challenge here is that correlational machine learning methods really is searching for data patterns. It's making a very simple assumption that the data patterns that it finds in its training data are going to be the same data patterns and should be interpreted the same way as the patterns it sees in deployment. The problem is that often the data patterns machine learning finds are spurious. What I mean is that the patterns aren't the same when we go from our training environment to our test environment. And when those patterns are changing, machine learning models fail. So, we can look at lab experiments where we take the MNIST digit recognition task and see the digit recognition accuracy drop significantly when we do something as simple as rotate the digits to an angle that wasn't seen in the training data. We see that the same thing happens in object classification when we see a 3D perspective shift. We as humans can take a look at the stop sign at different angles and recognize it each time, but a classifier that doesn't know to look for this makes really silly mistakes. And these aren't just about the kinds of, benchmark problems we see. This happens in the real world as well. So early on in the COVID pandemic, hundreds of labs around the world started building machine learning models that would look at chest scans, CT scans of someone's lungs to identify or diagnose whether that patient had COVID. And later studies found that looking at these hundreds of machine learning models that people built, people found that none of these models were actually fit for use. None of them could be deployed in the real world. And many of these models actually failed because of false correlations or spurious correlations. For example, to give you a sense of the kind of spurious correlations that these models fell prey to, one model was built on training data from a hospital that allowed patients to either have their chest scanned while they were sitting up or while they were lying down. The sicker patients tended to lie down. This meant that there was a correlation between someone having a bad case of COVID and lying down, and that, of course, would show up on their chest scans. This made the ML model more likely to identify someone who was lying down as being a COVID patient and someone who was sitting up as not being a COVID patient. And obviously, that does not transport well as you change your hospital policies. In another extreme case, all of the healthy patients were actually children. The healthy patients were taken from pediatric scans. This means that your COVID classifier actually became an adult versus child classifier, and again, did not work. That's not what you want to have if you're actually trying to diagnose COVID. This type of problem of data pattern shifting is particularly challenging for decision-making applications, because when you're making a decision based on the output of the model, you are actively changing the data distribution by construction of your application. So, for example, if we have a task that's going to let's say we define a task to help us decide when to irrigate an agricultural field based on predicted soil moisture levels. If an ML model tells us that the soil moisture level is going to be low, we will irrigate the field so that the crops don't die. We can train this on our AI models on years of sensor data from real fields, and then ask the question, it's going to be very hot in a couple of days. Do I need to water my fields? And the model will say, no, the soil moisture will be high. I've learned that when the temperature is high, the soil moisture is also high. This doesn't make any sense. Why is the model giving us this answer that doesn't match our common sense understanding? Well, it's because the model was trained on data where the farmer always watered on hot days. This means that the model learned the pattern that on a hot day, the soil moisture level is high. And when we now go and change our action policy based on the results that we're seeing, we're breaking the patterns that the model learned by construction. And this happens or can happen in almost all decision-making applications where we're intervening on the system that we're measuring. So we can represent these types of challenges a little bit more formally. We can draw out a graph that relates each of our variables to each other, and draw arrows that indicate the direction of causal mechanisms that we believe might exist in the system. And when we have a policy here, the farmer's past irrigation policy that relates the temperature to the irrigation, and then we're trying to predict soil moisture levels, what we have is an underspecified machine learning problem. And that's what leads us to issues. We can do a great job predicting soil moisture, but as soon as we change this farmer's policy, we're going to run into problems, because we won't know how much of this outcome, the soil moisture, is caused by temperature versus irrigation. In a sense, what we want to do is take this joint distribution that we're observing over these variables, and we want to instead predict this joint distribution on the right, where temperature in irrigation can be arbitrary and independent of one another. Now, we can do that with causal methods. Take this data, our assumptions about the underlying causal mechanisms, and then identify a strategy and estimate the result that we want. There are going to be a couple of fundamental challenges. I won't get too detailed into the methods because I want to get into the software package and the applications. But I encourage anyone to reach out, and I can provide more details about the underlying methods as well, or resources to learn more about them. There are two fundamental challenges that come up for causal AI, though. One is that we need to, in order to correctly identify identify these relationships from observed data, we need to be able to have some domain knowledge about the potential causal mechanisms in the data set. It turns out that if we're looking at data alone, that's usually insufficient for identifying the underlying causal mechanisms, because it turns out multiple causal mechanisms can be fit to a single data distribution. The implication is that we need some knowledge that comes from beyond the data itself. Usually we talk about that coming from a human expert, a domain expert who understands the system. But unfortunately, those assumptions are often difficult to validate without experimentation or a fair amount of work. So that changes our underlying analysis process as compared to conventional machine learning. The second issue is that we never observe the counterfactual world. If we're predicting that soil moisture level is going to be high, even if we don't irrigate, and then we decide to irrigate, we're not going to know what would have happened if we hadn't. And so this makes it challenging to use standard machine learning validation processes like cross-validation. Instead, we have to come up with new ways to gain trust in our analysis and its results. So, just a brief recap: causal AI is about guiding our AI models to focus on the underlying causal patterns, capturing the mechanics of the system. The purpose is to allow us to better answer cause and effect questions. Though we, in this regime, we do have some new challenges around how we capture causal assumptions or domain knowledge, and about how we validate or refute our analyses. So, to help people apply causal methods to their decision problems, we have been building a suite of open source tools and are continuing to grow these out. The design principles for this software really focuses on three high-level principles. One is that we want to scaffold our causal analysis process for practitioners to make sure that it's easy for people to apply current best practices. In particular, we focus on how people express and validate causal assumptions to ensure that the analysis results are reliable. Because we know that the technology is going to be changing over time, we try to separate the statement of the causal question itself from the underlying algorithms and implementations. This is intended also to help it make it easier for researchers to come in and plug in new analysis algorithms under the covers as well. And finally, we recognize that causality has been a field that's been studied across a variety of disciplines, from statistics to computer science to econometrics, and others. And so we are trying to really bridge across these different causal frameworks with common abstractions. For the specific task of effect inference, and then we can generalize this to other tasks, we focus on a four-step process where first we ask a practitioner, an analyst, to come in and model their system. They bring their data and they bring their domain knowledge expressed as a causal graph in their first step of the analysis, and we make it easy for them to express their assumptions in this step. Second, in the identification step, we analyze the assumptions that someone has expressed to identify valid analysis strategies to answer a causal question. This identification is usually an automatic algorithm that, given a causal graph, tells us how we can estimate what we want to estimate from our observed data. Once we have a strategy, once we've identified a particular causal estimand, then we use an effect estimation algorithm that really is a statistical estimator trading off variance and bias questions, based on the assumptions we're willing to make about functional forms, etc., to get us the best effect estimate for the problem we care about. And finally, we go and look at all of the assumptions that we've made throughout the analysis, the parametric assumptions, the requirements, any additional requirements made by the identification algorithm, and the initial assumptions that the analyst brought in the form of their domain knowledge. We validate these when it's possible. We try to refute them otherwise, and then finally, if we can do neither of those, then we run a sensitivity analysis so that the analyst has a sense of how much their answer might change if that assumption is wrong. Our core open source library is DoY that focused on the scaffolding of best practices. DoY is right now the most popular causal library on GitHub with a couple million downloads, and we see it being used in third-party tutorials and courses. I'm very happy, most happy perhaps, about the open source community that we are growing with over 60 contributors from across academia and industry. And we understand that there's broad academic and industrial usage, including production deployments. In addition to DoY, our suite consists of several other libraries and tools. The EconML library is focused on the latest causal ML approaches for sophisticated estimation methods. Causal is a library that provides deep learning methods for causal discovery and end-to-end inference. And then a new tool called ShowY provides a no-code interface atop these libraries to make it easier for people to use these approaches without having to code in Python. Setting these tools in place across our four-step process, DoY and Causal help with the initial measurement and modeling of a problem. DoY provides the identification algorithms to help you translate your assumptions into a specific estimation strategy. EconML provides the most advanced estimation methods, and then DoY provides the validation approaches to test all of your assumptions. In the interest of time, I won't go through this code, but I hope the fact that I can fit basically all of an analysis process on just one slide gives you some sense that it's not too hard to do. About 9 months ago, we shifted our DoY library into a community-driven organization inside GitHub called PyY. So it's github.com/PyY. And the mission of this organization is to really build an open source ecosystem and encourage the broader, our friends across academia and industry to trust that this is not just a Microsoft project, but really we're welcoming of all contributions. And we're seeing that message coming through, and I hope if this is something you're interested in exploring further, you take a look. We have seen a growing number of research contributions, including most recently Michael Oberst from MIT providing us an additional analysis support for characterizing overlap and population support in causal analyses. And Kun Zhang and his team from Carnegie Mellon have contributed their Causal Learn library, Python library for causal discovery. And many other algorithms have been coming in as well. And we've also been seeing more people contributing to documentation and tutorials, and really seeing a vibrant community coming together. I'll touch briefly on where we see the biggest need for research based on what we're learning about usage, but I won't go into these. These are the topics of other talks. But really, we see the number one frontier challenge as being that people have a hard time encoding their domain knowledge as a causal graph. And so we think there's a fruitful area of research here looking for new sources of domain knowledge and tooling to help people express their domain knowledge in different scenarios. So, of course, deep causal discovery algorithms is an area where we're interested in. Also, using trusted simulators to provide way to bootstrap a causal model, and based on sometimes decades of experience that have gone into building a trusted simulator. And we are starting to look at the opportunity to extract domain knowledge from large language models that have captured a reasonably strong characterization of the world. A second research frontier is about extending causal analyses to work over high-dimensional, unstructured data, such as text and images. The key here is how we disentangle high-dimensional data to match the semantics of cause-effect mechanisms when we know that there's multiple factors that are going into an unstructured image or text. The third frontier is about continuing to improve our approaches to validation when we don't have ground truth labels coming from that counterfactual world. And so here we're looking at how we can do empirical validation of methods with A/B experiments, such as with online monitoring when it's feasible, and how we can continue to improve our sensitivity analyses and analytical tests of core assumptions. Some of the at this stage, I'll transition to the third part of the talk, just touching briefly on some of the decision-making application examples or scenarios that we've been seeing people apply these methods for. I'll just say in one slide, our own first-party experiences were the most advanced in applying these causal methods to advertising in Bing Ads. We've motivated by the desire to minimize the cost of A/B experiments in these scenarios and to enable us to run the large numbers of virtual A/B experiments, you might say. We've been transitioning the back end of our modeling here towards more causal approaches. One paper that we published a couple of years ago at Wisdom in 2021 is our work on robust click prediction, a new algorithm at the time, causal transfer random forest, to combine experimental and observational data to improve our offline click prediction so that we could do better estimation and tuning of system changes. And more recently, we've been working on estimating the effect of ad campaigns on user behavior, on conversions at scale, and the work needed to make that real. DoI and PyY and the associated causal suite are being used much more broadly in industry and academia across a variety of domains, from health and medicine to logistics to manufacturing and education and others. These are just a couple of paper headline titles that I've seen in the last month or so. And it's really exciting to see the variety of problems from, civil engineering to health and environmental safety that people are applying it to. At a higher level, the kind of classes of scenarios that we see come up most frequently is I'll give you the top three. The first one is people asking what are drivers of their key business metrics. The setting is one where a user wants to optimize some metric, profits, customers' happiness, or something else, and the user knows that they can control a number of knobs, and they want to know what is the causal impact of each of these knobs on this outcome, so that they can go and explore the right knobs and prioritize the most promising knobs for in their future experiments, in their brainstorming about how they might be able to affect these knobs the most efficiently or cost effectively. The challenges we see people have is, of course, understanding their domain assumptions. How do these knobs relate to each other? How is their effect on Y mediated in many cases? And also ensuring that the data that they're observing is the same as the manipulable knob they have as well. The second scenario that's quite common is when people know that they have a program that they want to deploy or have deployed that they won't be able to run an experiment on, such as a customer loyalty program or a membership rewards program. It turns out that many companies, or customers rather, don't feel great when they know that someone else has gotten a reward when they haven't. So this makes companies hesitant to run an A/B experiment with the membership rewards or other kind of discount or benefit program. But then that leads to the problem that when you see a change after you deploy your loyalty program, it's difficult to identify whether the impact of that change is due to your policy or something else. There's a number of methods that people can deploy here: synthetic controls, encouragement design analyses, matched analyses, and our library helps you run all the appropriate ones for your problem and come up with an estimate of what really the impact of the loyalty program of the policy change was. The third scenario is about recognizing that it occurs when a business recognizes that it has to adapt to a changing world, and where they know that they're going to have to extrapolate or generalize from what they're seeing today to a future world that's a little bit different. And they want to make sure that their extrapolation, their guesses about what's going to happen in the future is robust. So, for example, we see people asking questions about how climate change is going to affect their business operations, where temperatures are going to be different than what they've seen today, and they want to identify the controllable drivers that might mitigate the impacts of that change. Simply predicting outcomes based on observed data so far has the problem that it's going to potentially confuse correlations going on today with the temperature shift that's expected to happen in the future but hasn't occurred yet. Those are the three scenarios that we see as being most common, but really the tools that we've built are trying to help people express most any causal problem as a graph and then apply a set of advanced algorithms to solve that task. There is a there is a gap from that domain question to the causal language that is where a data analyst has to come in and help make sure that a problem is framed well. Our software is trying to raise the level of discussion to make it easier for that data analyst to be confident in their translation and in the final results that they see. If I have to highlight a couple of takeaways, I'll say that, please take away that causal AI focuses on causal patterns as opposed to spurious ones in your data, that this is particularly critical for decision-making tasks, and that if you're looking for tools to help you scaffold your step-by-step best practices, mix and match some of the advanced algorithms for discovery, identification, and estimation and validation of your results. We have an open source causal AI suite for you. And if you're on the research side, I hope that you'll take a look and see if there might be a way for you to learn from practical usage of your research, and if there's something we might be able to do in this ecosystem to help you do that. So I'll close with links and a thank you. In particular, thank you to you, the audience, and also to the whole team of collaborators who have worked on this causal suite, both inside Microsoft as well as our collaborators in the open source PyY community as well. So thank you very much. If there are any questions, I'd be happy to take a moment. I don't know how much where we are in time, but.